year. And so you see that, so these are by the regions that have the most timberland. So it's the south, much of that is mainly conifers. The north, including all the way over to Minnesota. Then the Pacific coast. So you see under the timberlands, there's 83 million, then 66. But most of these are not plantations. So on the two yellow columns add up to the timberlands. In the United States, most of our forests are not plantations. They're natural trees that grow there. They planted some of them, but often trees seed in there, and they just become managed like they manage them for the longer rotation. So I'm going to be focusing here on the West Coast, where we really have about 26 million hectares of natural timberland that are managed, but they're pretty much using the same trees that were there 10,000, 20,000 years ago. There aren't that really many plantations out in the West Coast.
So you harvest this 2011. How much of this timberland, all these trees are being harvested?
So of the 211, most of the private land gets harvested at some time, and then 15% of the national forest land, so 150 million, something like that. It really varies by region.
What's the distinction between total forest and total timberland?
So forest is like any place that has trees on it. So that includes timberland, which is highly productive timberland, plus reserve forests, which are national parks, 40 million, or wilderness, plus land that basically the trees grow so slowly, they're not considered timberland. So the classic is the interior Alaska. 46 million hectares of forest, and only 3 million actually grow fast enough that if you had a road there and everything, you would actually be worth doing something about it. Yeah.
So you said that the trees take like 100 years to grow?
But you
in the case of the Pacific Coast?
We grow them that long because we want big wood, yeah.
So what's the like natural turnover time of the Pacific Coast forest? Like if you just let it go, how long does it take for it?
Well, we're going to get into that. So trees on the West Coast, you often in the stand you'll start with, we'll go in the forest, they'll start with like 5,000 little seedlings after a wildfire. And then some of those trees can last 500 years. But of those, originally start with 5,000 trees, they'll probably, at the end of that, when they're 500 years out, there's only going to be maybe 20 trees left. So something happened to the other 4,980. So the winners can live a long, long time here in the West, but most of the trees never get that old. And that's kind of the trick. The mortality question is a part of this. Because a lot of people say, well, if a Douglas fir can grow to be 500 years, then every tree I planted is going to grow. And it's just, I've done analysis, and most old growth forests in the West have, I think it was 30 trees plus or minus 10 per acre. That's all. And they started, in California, state law requires you to plant 300 seedlings to start with. So basically you're guaranteed you have to kill 270 of them. Someone's going to kill them, either the bugs or you if you have a chainsaw. Or me, not you. So the key issue was I was trying to find a simple characteristics like which regions have how much of what I call big tree forestry. And to have big tree forestry, you have to have big trees. And so given that I brought in a 21-inch diameter log, I just used what percent of the total volume by region is in trees bigger than this. And so you see only the Pacific Coast has over half its volume are in really big trees, and no other region is anywhere close. Most of the trees are younger. In the East Coast, the average stand is only 47 years old. In the West, they're twice as old. So it's very different. So the West Coast is very unique in that way. So we still have a lot of trees, and even though like Michigan, we cut all our trees down, ours actually regrew. They've had a very hard time getting those great pines back in the upper Midwest for reasons I don't understand, but they really have nearly none.
In the South, you have 83 and 20% is about 18. In California,
right.
It's about 16. If you compare this 18 million hectares in the South versus the West Coast,
right.
Is it the same type of quality?
So because of the basically the thinner soil in the South, the trees start really fast, but after about 50 years, they just don't grow any taller. And so from forestry, we just cut them down then. Whereas trees in the West Coast will just keep on growing. And it's the soil depth, they just kind of run out of nutrients, I think, because they've got more sunlight and they have more water. But they just don't, genetically, they're not made to just go forever. redwoods and sequoias are basically just made to go forever. We don't even know when they're, they don't get old. I mean, the ones that are still alive are still growing. I mean, they're 3,000 years old and they're still putting it on. It's pretty amazing. But yeah, so I think we're going to get at some of the story of where this goes. And this is another, I was trying to look at kind of where is kind of an idea of kind of physical productivity, and I kind of looked at, well, if the plants are, as I mentioned, just evapotranspiration of plants is kind of, well, I'm not sure how efficient they were, but just where is growth, and that's on a scale from 0 to 100, centimeters of water were, per or something was released. So anyway, you see in the south is really where we have the best growing land. It's in that 90 to 100 area. Where I'm going to be talking about is here out on the west coast, where we're really about only 2/3 or half of that. So we don't have that. It's colder, snowy, we're higher latitude. But our trees get really big because they grow for many more decades. So visually it looked like we have a lot out there, but it didn't really put on as much. This is the area where if you're looking for growth per hectare per year, it's going to be in the south. And it's by a long shot the difference. And so this is just some examples of what I'm talking about, big tree forestry. This is a field trip I took my forest management class was, and that guy, he got a 5-foot long chainsaw. This tree was over 6 feet in diameter, and I counted the rings. Anybody have an idea how big this redwood, how old it was? It was over 5 feet in diameter. 78 years. But it was grown in the middle of an open grassland. There are no trees competing with it, and it just got all the resources and then just shot up. And it was. Huh? They didn't do the cutting. No. The real guys are around the corner. He was just trying to pick this thing up. That's what he's looking at. He didn't cut it. No, he was like, you can tell he can't even raise it all the way up. These are. I mean, I have a big chainsaw, and it's half the size of what these guys had. It was pretty amazing. I have never seen a chainsaw that big. But they still make those and use those in California. These people actually have these 5-foot long chainsaws. And then this is another picture. This is one I know a little bit more about. This is a forest going into, we have a Blodgett research forest, and in the summertime we have like 45 researchers that are studying entomology, soils, atmospheres, chemistry, i.e. these aren't foresters with fire training. And if we have a fire, we have to get all those people out safely. And so we have a mile-long entry road, and we don't want to have kind of a wall of, a tunnel of flame there, so we basically have thinned out most of the trees. We've gotten it down to only 30 trees per acre. And it pretty much is purely for public safety. And we didn't really think, we actually took it out of the timber base, we stopped measuring it, and then I went back and tried to figure out, well, how's it doing? And lo and behold, it was actually putting on about 85 to 90% of what a fully stocked stand would. That's all in these really big trees, most of them is 32 inches in diameter, most of those trees, over 150 feet tall, and we're still growing those to harvest those. As after they have a mistletoe, we're taking them out. But that's just an example. It's a very open stand. But totally different than what people think of a plantation. But this is being managed. We harvest it every 10 years, and we make quite a bit of revenue every 10 years when we do it. Because these trees can still put on, they're about 100 years old. They're still putting on a considerable amount of growth, and they're really not, a lot of these they're not slowing down now. But that's kind of an example of the way you can actually manage these stands. But you can see we've cleared most of the underbrush and the smaller trees out to make sure if a fire comes through, there won't be much to burn except the litter. But this is still a kind of a managed stand. Very different than what people think of where you're going to get bioenergy. So what I'm going to go now is, one thing, when I've looked a lot of the literature, in the Forest for Bioenergy magazine, everybody assumes, they say, well, forests in California or somewhere else, they assume all the ownership's the same, all the management's the same. And in California, that's not the case. And that's one thing we'll go into is like the differences. Even if you have the same forest, the ownership really matters here. And so this is that's our Blodgett forest, and you can see land is still owned on the original square mile grid we put out when we first had the land. And so here you have this checkerboard, and you have some more up there. That's when the land we gave to the railroad companies to convince them to build the railroad. So they got every other section all the way through here. They combined it. So the green here is the Forest Service, and the blue is one timber company. The yellow is another timber company. That's another timber company. So you have the same forest type with different owners right next to each other. So it's actually really nice for an experiment because conditions. You're not comparing Brazil to Germany. You're comparing you just walk across into the next one. But you get some real variation in who owns kind of very similar forests, very different views on what they're doing in. And so I think this gets at one of the questions on kind of what the flux is. I went back and tried to look at the data, what happens to forests as they grow. If you just take all the forests in these different regions, the north, and then I looked at the comparison of private land versus National Forest Service land. So in each decade, these trees grew. So what happened to that growth? So the green is that the trees got bigger. There's more inventory, more carbon in the forest. The wood-looking one was harvested. And then the gray is the mortality, which often is not considered because no one likes it except, no one really likes to talk about dead things. So they just kind of ignore it. But I think when you really look at this, what I see is that even though the green bars are very similar, for instance, for the north, that basically 60% of that growth over a decade stayed on the tree. The private sector did a lot of harvesting, and they had the mortality. But the national forest, if you harvest less, they still lost just as much wood, except they just didn't harvest it. So you see the same pattern that in the south, that they're similar, but it's just all mortality. In the Rocky Mountains, all mortality, it's 3 times as high. Similar, 2 or 3 times as high out here. So the mortality, which often if you look at people, I've dug in a lot of the ecosystem models, they just put in they make up a mortality index and they put it in the model and they assume all forests have the same mortality loss. And then they put a harvest on top of that. What this suggests to me is it's either harvest it or you let it rot. One of the two.
Mortality here is not in terms of tons of biomass.
It is.
Numbers of trees. Oh.
No. So this is all volume.
Okay.
Volumetric. So what they do is the Forest Service goes back and measures the trees, and if the tree's dead, they say, they look at how much volume of it is in that dead tree, and if they see the stump, they say, that volume went to the mill, and then if it's a bigger tree. So it's...
So the mortality is basically I can develop an index of efficiency, let's say.
Right.
So basically I say, okay, only 70% efficiency because 30%.
Right. Right. And so you still have carbon there, but once you have a dead tree, it's slowly rotting at a certain...
So the carbon goes...
just a little bit, because, a tree dies, and then it just dies, and, it's still there, and then just as the microbes eat it and do all this type of stuff, they're going to basically be aerobic, they're going to be breathing, and so that's when the CO2 slowly goes up. I model it with just a half-life decay function, so you still see it, and after wildfire is the same thing. Wildfire comes through, that's also mortality. So we'll get into that. But yeah, you can actually think about these. Well, so one thing you see is this, nature is a pretty inefficient system if you're just looking at carbon, because, they're putting, this looks like, this is just a static numbers, because they're just looking at the number of dead trees in this year and the number of dead trees, because there were some trees, the dead trees, some of them fall over and then they go out of that system. But foresters have this really weird way of calculating stuff, and we then tell people all this weird ways we do stuff. And then people just use the numbers incorrectly.
This could be a very easy way to reduce greenhouse gas emissions.
Right. Yeah. Well, so this is kind of one of the principles of forestry is basically we try to kind of consider kind of ruthless, but you cut the tree down before it's going to die. So they're still alive, it's still green, but it's like if you see mistletoe or something, you paint those and you take it out, and that's really efficient systems are but you have to look at every tree, and that's expensive. But so this got me to thinking is like, well, we really do need to dig a little bit more into this mortality harvest issues. And so this is going back, this is another piece, we have that land I told you at Blodgett where we know the whole place was clear cut. We know that we grew the forest back. We've harvested 1.5 times the amount of volume that was originally there, that's there now. And the next door to us is the National Forest Service, that they got the land, they never clear cut it, they slowly manage, they've taken out a little bit of wood over time, just hunt and pluck. And then we also have national parks that never have been harvested. And so what I did here is I looked, okay, let's look at all high sites, high quality land, deep soils, good growing conditions. What do we have now, given that, we have very heavy harvesting, light harvesting, and no harvesting, how different are the inventories? And the difference in inventories is pretty small, given that we've taken out 2.5 times the one on the left side. And it's only about 20% less than the Forest Service, which had a little bit. So we just, in kind of a rough calculation, when you include what's there, the growth, plus what we've taken out, my calculation is that Blodgett Forest is right next to the National Forest land. It's been 3 times as productive as a carbon machine because it basically just kept on harvesting it. And it's nice. We actually have this data. You can go back and see these plots and look at them and say, what really happened here? I can't historically go back and figure out what they did with the harvested stuff. But from here on out, we can actually think, well, how do these systems work? We do have some longer-term numbers. So this got me thinking we really need to figure out, well, what happened here? I mean, why aren't these growing a lot more? And I think it is back to the issues of mortality. It's a lot, both fires and non-fires. You're going in there and taking a lot out. But this is the kind of idea. I was just looking at one period of data. I'm not really sure what was going on. So what we now finally have, we just finished this year, the National Forest Service. They put these plots out in the forest, and they measure them, but they did it since 1940s, but every year the bureaucrats in charge and politicians, and they changed the plot design, so they're never actually measuring the same trees. And so there's all this covariance problem, so they never could do this. Well, they finally, for the first time ever, they measured the same trees a decade apart. So we actually have this very detailed analysis of what happens to land, and they measure on all types of forest land. And so over here you see, this shows in a decade they measured all the live trees, and then they figure what happened to that volume. And so you see that that's not the greatest color system because Excel changed it, but the tallest bar for the California all, the largest chunk went into mortality. A very small piece in the middle went into harvest, and then the last green one, which had been reversed, that was the growth in the forest. That's the net inventory change, the added carbon. But what's really I found interesting is that how different types of ownerships are. The California timberland, they're harvesting a lot. They still had pretty high mortality, which is interesting, but they didn't add nearly as much addition to their stock because they kind of figured they kind of have an optimal machine going on. Families, in this period we had the big recession, 2007, basically when that happens, families just don't harvest. They wait for the trees to grow. So they harvested very little here. So they've added a massive amount of wood on their land. But then the National Forest Service land has even this mainly, most of their growth was going into death, which I think is kind of an inefficient system. And you see even in the reserve land, they even actually lost carbon because they had so much mortality there. This is a lot of big wildfires we had in California. So just so we actually start to have data, we kind of understand how these systems work, thousands of plots, and so we can take standard errors.
Do you have any information about environmental services? Maybe that they believe that this will deliver?
Yeah. So they're less good for the living. That's not a big issue because the soils have so much soil carbon. Their biggest value is wildlife habitat. So standing snags, the birds like to chew in there and live in there, and then once they're holes, then that's where the fishers go. When the trees fall down, that's kind of where the salamanders hang out. So it's critical to have. I think one of Ford's friend of mine said I need to have unhealthy trees to have a healthy forest. But you don't need to have as probably as many as the Forest Service does. Yeah.
Does this suggest that we should be doing different things to manage the reserve forests in order to prevent fires from happening?
No, I would say that the reserve forests, maybe they put out fires for a long time, so they just might have more than they should given the chance of lightning strikes. We manage those for really biodiversity, so to think we should actually put in roads at high cost and then take out these little scrawny trees and make a mess. No, I think there's really no, and this is like, there's a reason why we did this is a policy decision we made in the United States to put them off. And when you actually operationally, I've looked at this stuff as like, if it isn't roaded, don't even think about it. And so these aren't roaded, and so they're basically, the timberlands though are roaded. They've been used before. So those are ones that you can put those online with a flip of a switch. The reserve land is pretty much, it is what it is. And it's also lower quality land. And so this I tried to kind of show them, I just stacked them back up as a bar and just to compare them. And so what this is the total productivity. So you see the private lands, they were more productive lands. When George Weyerhaeuser and John Blodgett came out here, they're pretty smart. They found the best land and they left the bad stuff for the Forest Service. The corporate land actually is lower than the families because the corporate timberlands they have a lot of east side pine, which is low rainfall, not real productive, but nobody else it wasn't big enough for family to own it. So that's why their average is lower. So you can see the national forest lands are a little bit less productive. pretty much based from soil productivity. But you kind of see kind of the breakout where, you know, where you're allocating as a system, kind of where you're allocating it. And so this is a little bit different. So now what I've done here is I put them all on a percent of the growth that happens in a decade. Where does it go? And so here you see the timberlands. There's the blue is the gray is the natural non-fire mortality, which is about 20% of the growth. That's about as low as anybody seems to be able to get down to. Then you see the red is the fire mortality that's still there. So more trees died, but some of them were harvested. But then you see the Forest Service, you know, they lost a lot to wildfires. But most of the mortality is not to wildfires. It's to this very sexy bugs, root disease, defoliators, all the stuff you can't see. But when you actually add up the volume, it's the non-fire mortality that drives the system. And I actually went back and I found many, many papers where it claimed the only mortality worth measuring was fire perimeters, and they got it published. And you would think forest ecology management would be a little bit more thoughtful, but they weren't. But you really see basically, if you compare the timberlands here, that they're losing nearly 60% of that net primary productivity to mortality, as opposed to 20% here. The industry with this pre-commercial thinning is if there's too many trees, they take out basically whole rows of trees to try to let the other trees remain bigger. But they never were able to find that random mortality in the forest, because corporations, their midterm harvest is they want to harvest where they're going to put the road in at the final harvest, so they don't look for the dead trees. They just are putting in the road system when they come back 40 years later. So some people actually do go out and find that mortality. You probably could actually, if you're really in the east, New England, sometimes they actually go out there and they mark the trees. The trees are really valuable and get that down to a much lower number. But I was really surprised how much of the system, and for people who work in annual cropping systems, to talk about 20 to 60% mortality is fairly shocking. It's not even expected.
The value of the wood, I don't think the value of the wood is not to be worked out to be the tax. It's actually
right.
Fruit and vegetables. If you have high value crop,
yeah.
You have very low.
Yeah, so basically I go on these lands all the time, and you just see the guys going with the chainsaws, and they just cut down every tree, and they leave them, and some of them are quite big-sized trees. I mean, they're 6 to 8 inches diameter, but they're just not worth taking out because there's no bioenergy plant nearby. So it's nearly worthless, and that shows you it is worthless.
What's the difference? You mentioned that the East Coast forest trees are more valuable, but it's just better building wood?
So no. In some areas where you have valuable hardwoods, like walnuts and ashes, the individual tree is worth a lot of money because it's turned to veneer and things like that. So their foresters actually go around and look at individual trees and mark them and kind of remember where they are. Here, where basically our trees are all kind of commodity trees. We make 2x4s, 4x6s, 1x10s, but we don't have high-value hardwoods that you make veneer out of. I mean, we have plywood veneer, but that's not the same value. Redwoods is more valuable. Yeah, people really, that's kind of unique for fence posts, but yeah, this is. But you see this ratio of basically 20% mortality on private land to 60% on federal land is exactly what Andy Gray found for the Pacific Northwest on 2 other studies, but the similar types of data sets, but different plots up there. He had private land. They pretty much are adding no inventory. They're doing lots of harvesting, but 20% mortality. And then the National Forest Service land is, about 60% of that growth. I was shocked at this. I always thought these are big trees. They can last forever. It's like we don't harvest. They must be adding lots of inventory. They're barely adding inventory. We did this 25 years ago. We stopped harvesting to grow big trees. We're growing snags. Yeah.
Super important in the carbon, and you can really see the carbon loss.
Yeah, this is volume, so it's proportional to carbon. Right?
That would be great.
Yeah, it's a lot. So then, it turns out this kind of shift. This is all interesting, but when you file a timber harvest plan in California, you have to measure your carbon impact, David. Every permit you get, you have to write in this thing, and the state wasn't really impressed with their own, so you can write your own. So we've tried, as a cooperative extension, is try to create a methodology that's both transparent, based on data, and reasonably cheap to do. So what I did is I took those FIA plots, and this is the ones similar to our forest, and you can take this website and you just go down to California mixed conifer, and it pulls up 1,397 plots. So you basically have a statistical approach, and then figure out how those forests grow, and then they give you these nice little pictures of what the trees look like. Yeah.
Anyone does it internationally, because I tell you, why. If you can show that you lose more carbon from death rather than all these fires in Indonesia, then that can be huge. Because if it's elsewhere.
Yeah, I just started working with this, and when wait, how can this be true? This is mortality. I'm not an ecologist, but I do think,
really
there's a lot of stuff going on here that isn't. Yeah, and where we have really good data on this is the United States and Europe. I'm really not sure how good the data is in Indonesia. And hardwood tropical systems, actually, they probably have more loss to mortality. But anyway, so this is an example of using this, modeling this for us, and then making sure the difference between what foresters measure is those board feet to the total biomass, that it's proportional, but it's a different measurement. So we double check the data that it's actually correct. And then how fast forests grow, and this really shows if you let a forest grow, just how productive redwood forests are in California. This is a mixed conifer forest, and then the pine forest on the east. That's more than 2.5 times as productive redwood forests in California than the Sierra. It's really quite astounding, those forests. But so then we put those into some of the models. But when I started looking at it, it's like, okay, I know the forest is growing. I can model that. It's like, what happens when all this wood gets cut? What's the life cycle analysis? What happens to it? And I went back when I started looking at this. There's all these tables. They're called the Department of Energy 1605B tables, where it was kind of a life cycle analysis. And there's these really pretty little Excel spreadsheets everyone could download, and everyone did download them, and they never bothered to find out where the numbers came from. But I was looking at it, I was like, wait, I live out here, and they're telling me that in the sawmill, if 100 tons of saw logs go in, that there's a pile of 16 tons of sawdust in the back 40. Which is illegal in California. You couldn't do that from water quality. It's like, how can you do this? And all the numbers have this very high number of loss. And I called up, where did you guys get these numbers? And I went, well, I don't know. It's some paper. I'm not sure. And then they said, well, once the wood is used in society, how long do people use it? Some of it goes into houses, and the houses last for a long time. They do remodeling. They burn down. Some goes into paper. And then some never gets collected, never makes it to a landfill. And they also estimated that 35% of the wood used in society just ends up as waste sometime in its lifespan. And it's interesting that California is the most wasteful system in the United States, which I thought we have a little bit stricter environmental laws and landfill laws. It's like, what's going on here? So I called up and I checked. Well, it turns out all of our waste paper goes to China because they bid for it. So nothing goes to the landfill. So if you're only counting U.S. California carbon flows, what didn't make it a landfill, so therefore it must be waste. Anyway, so you get some fairly large errors when these kind of assumptions. Well, it's because it's a national publication. We'll just put it in, and it's really, the spreadsheets are quite easy to use, even though they're wrong. But as I went back and looked, it's like, well, what do we know about how the wood's used? And this is a picture of the the Forest Service. They go out and they measure all the wood, where it goes to the sawmills, the veneer, and the efficiencies. And they get about a 99% efficiency, as opposed to that 84% efficiency. And this is the same entity. The Forest Service produces every 5 years. They do these studies, but they've never been integrated into national numbers or any of the life cycle analysis. I just saw that GREET publication. That was a 2014 publication. They used a 1996 publication plus a personal communication to use their numbers. So it's like, wait a minute. I think there's a little bit of difference here. Maybe we should actually get the numbers right.
So do you need help interact with GREET to get their numbers right?
Well, it was weird because GREET is about, they're doing a thing for, if you did willows, the GREET can do, it was a little bit hard, I was like, I don't think.
We're well connected.
I think, yes.
We can help fix it.
Yeah, and I've talked to people in the Forest Service, and they're so busy writing other publications. When are you guys going to update it? They actually have all the new numbers, not just for California. But I think it'd really help out if we got all this life cycle stuff right, because the Forest Service has just an amazing high-quality information on this. But this is the difference when you look at kind of the life cycle analysis in this C Club, where they think that the products went. And they basically have, 40%, if you cut down the trees, 40% is waste right off the bat. Then society wastes another, over a 100-year period, they waste another 18%. And these are the only two things they say are of any value, 42% of it. I did some work with Gary Nakamura. We actually tracked some harvests and some mine sites, and we found a lot more wood stayed in products. A lot of stuff after it's used end up as bioenergy because we have a lot of urban waste-to-energy plants. And there's a lot less waste because it's actually illegal in California to waste that much stuff. You'd go to jail for that. And here's an area where there's a very high fire risk. They really didn't leave any logging residues there because of the fire risk. That was kind of unique. But you really see how big the difference are between saying there's really only 42% of the system is useful versus we measured 93%. It's a pretty big difference. I think it's a factor of 2 roughly. And so, what's one thing we're trying to look when we do our timber is thinking about the pieces of it. How much of the slash do you use for energy? How efficient is the mill? There's all these different estimates. You can use any of these things when you file your permits in California. How efficient is society as they're using products? Are wood going into good buildings or not? And, is carbon bioenergy considered? It's ignored by ARB, but they might change their view now that EPA changed their mind on this, or went back. They never changed their mind. I guess that's what they did. So this is one thing we are just trying to follow through, kind of, for our is track through where does all that carbon go. And so this is just an example. I look at a place. Well, what if sites where you basically leave 75% of the logging slash on the site, but then it starts to decompose. So I have it decomposing on a 20-year half-life. Then the tree regenerates. Then you kind of look at, the wood that's used for energy, these pink bars, these products, goes into landfill and try to kind of track it, but tying it back to those growth charts from the original tree and some of those numbers. And this is, if you just left the forest grow there, as the insects got to it and things like that, is just compare the values, the 2 life cycles on the same forest site. I think this from a bioenergy point of view is that when I compare these 2 models, that if you just let the forest grow, it's definitely going to have more carbon out there in the forest. I mean, trees in California keep on growing. They're not, even without level mortality, they're still going to grow. If you cut them down, on average, you'd have less. But when you actually do the math and you think about after products are used, then they're used for energy again, that bioenergy is the #1 end use for wood harvested in California. It's bigger than wood products, it's bigger than waste, it's bigger than storage. So it's really the thing, even though it's not worth much, that's actually where most of it goes. Yeah.
So can you tell us a little bit about how these plants and how they make energy out of wood and how much total energy it is?
So most of the wood is used for industrial heat. So it's used for drying the wood and doing things like this, used in drying agricultural products. But some of the other wood, it's chipped up when you go to these sites. They're all the tops of the trees and the branches, and they have these big chippers, and they just turn into little chunks. And they take that to these big 20 to 30 megawatt power plants, and they have a grate, and they just dump the stuff on the grate, and you can look through the little mica glass, and it just burns it, and it runs the GE boilers, and it turns into electricity. So California, ours are pretty old. I think Peter knows they're put in the 80s, right? Most of them. So it's the modern technology, the finished, they're about 3 times as big. They're bioenergy plants, but basically you just burn the stuff on a conveyor belt. And it's best if you can capture the heat and using an industrial process, then you have a much higher efficiency. If you're just doing electricity, you're losing that heat. But
so how much power is generated from biomass? There's about 600 megawatts involved.
Right.
Maybe about 300 at Long Line.
Yeah, California was a leader in this in the 80s, and now we've been passed up by numerous states because of the pricing difference. The wholesale price has been high. But it's a pretty well-known technology. It's really big in Oregon. In Western Oregon, nearly all the logging slash is dragged off and done this. They put a lot into their grid there. 15 years ago, they never even thought about it because they had all that cheap hydro. But then they have some nice new plants that are quite efficient.
And is urban wood waste going to those?
Yes. Yes.
So where does that get separated, or?
So the urban waste, they're under all these laws to reduce the amount of waste they have, and so they basically give money to they'll truck it from the Bay Area to a plant up on the Nevada border, which costs them $80 a ton to get it there, and they only get paid like $40, because they have to reduce their amount of landfill. So they separate out the stuff that has paint and stuff on it, but much of the urban waste is moved because they basically have to pay to get rid of it.
So when you say manage, you mean all the manage, all the stuff is managed?
No. So this is if we manage this forest, we did a commercial stand, and then the manage is kind of a scenario of managing the forest on this 80-year rotation compared to just letting that same forest grow. That's what this is. This is just those 2 examples.
But suppose you look at service, you do the same,
Right.
you do the exact exercise.
Right.
You let it grow,
Right.
service, basically, let it rot,
Right.
make everyone happy.
Right.
Private,
Right.
if we do the same thing as we did
Right.
before, I think the gaps would be much bigger.
Uh,
That is a relevant thing.
Yeah, it's a big gap, and I was the most shocked when we started to look at the mortality that the national forest in the West. I mean, these are big trees. I go out there and I see them. The trees are getting bigger, but I don't count the dead ones because I always look at the live ones. I guess that they've actually capped out in terms of adding carbon. It was pretty. The reviewers when they first did that, they just couldn't believe the numbers. They had to redo it 5 times. But yeah, they pretty much mortality has taken a much of the growth that we assumed was happening in the Pacific Northwest, up in Northwest Forest Land, and the same in California. And then they have more fires and things like that.
I think all of our models assume that
Right.
we live forever.
Yeah, so when you actually look at real data, you see both in the forest and in products, there's all these other, it's a little bit different. And that's what's great about the United States is we have all this data. It just happens to helps if you use some of it. Yeah.
Can the dead trees not be collected in biomass for energy?
They can. They once they start rotting, they've lost some of their stuff, and they usually don't harvest dead trees. A, because you need to leave some snags out there, and B, they structurally become weak and they're afraid of they're going to have worker fatalities trying to take down trees that might crack halfway across. So you don't really like to cut because the tree's 80 feet tall and you start to do something and the top falls off. So it's kind of risky. So actually, they pretty much right after a fire they'll go in, but 6 years later no one goes in and basically tries to sweep out all the dead trees because they break. It's just a cost.
It's hard to identify when it died. It seems like if it died in the last year, you probably wouldn't be that worried about it.
No, you're right. Yeah, the first few years it's okay, but yeah. So also selling it to these power plants, you really make nearly no revenue. That's what we found in California. We actually lose revenue when we do it on our forest. We lost $20 a ton, whereas we made $150 a ton for the lumber. So there's a lot of stuff that even the corporate side wastes because it just isn't worth them taking it out. And it isn't. They've done the calculations. I'll leave it there as a fire risk. It's not that big a problem. They may or may not be right on that. I just checked with my old staff that the burning rate in the Sierra Nevada in the 21st century is 3.5 times what it was in the 20th century. So all the professionals that came up, it doesn't burn that often. I've seen the statistics. It's like when you add up the rim fire, the king fire, there's a lot more stuff being burned now. People are really rethinking a lot of this, whether it's actually rational to leave so much fuel out there on the landscape. So this is just some kind of, because I think, just some ideas that, when we look at this in these systems, if you do some level of management, you can really outperform a no management system from a carbon point of view because I think it's really this uncounted mortality. When you actually count it, there was something else going out there that was kind of forgotten about. It wasn't really well managed. Yeah.
From what you say, I think that probably mortality is probably as big as fire globally.
Oh yeah.
Yeah, and because the
it's bigger.
Yeah, because the point is this: if you look at all what people are upset about,
right.
Is fire.
Right.
Indonesia. So my feeling is, if you can, that could really be
right.
very relatively very cheap strategy.
Well, tropical forest. Matthew Potts done some work. Some of those systems are not that productive because there's so much. The tropics are a great place for everything to live, including bugs that want to eat trees, and that's why there's just shockingly high levels of mortality. I mean, it's just trees just don't get that old there because they're just everything grows well. 365 growing days a year for your microbe. It's 6 feet of snow is really kind of slows a lot of our microbes down. Yeah.
Will any GMO type trees ever make an impact?
I think the GMO tree, that's those are usually more you're going to put in a plantation. This is kind of the non-plantation forestry. I think if we get GMOs, I think frost-resistant eucalyptus is probably going to be a big player, but that's going to be planted in plantations and it'll grow for volume. I think the one big issue is that I guess when I try to think is like when you're growing these really big trees, from a feedstock point of view, it's a very energetically inefficient system because you're basically growing green I-beams. There's all this structural rigidity, that all the energy is going into lignins and hemicellulose. It's kind of a waste of energy if you're just going to burn it. But so these big trees, the biofuel feedstock is only going to be kind of a secondary source. And right now it's a zero revenue source for us. It's kind of a cost, but I do think if you kind of looked at a system, you could probably get much more efficient system capturing some of these stuffs and actually, keeping the biomass plants we have running we don't have to build any new ones, just keep the ones we have running now. But
So the point is, if you look at that, and you look at panels with systems,
Right. Yeah.
and you also look at it not only from a perspective of
Right.
preventing
Right.
death, then I think without that much spending that much money,
Yeah.
really gain a lot.
Yeah, and you do on these systems, and these, these snags, the mortality in one way is bad, but it really is that's where the wildlife lives, and so you really need to be fairly. You got to figure out how much you need, how many unhealthy trees you need in the forest to have a healthy biodiversity. But that can be done, and the big companies, they measure every tree and they keep track of all this stuff. You can get by with a lot less mortality than we have out there. But that's one way is just the rule is just don't cut down. If the snag's been there a while, just leave it. So from a safety point of view, and actually that's kind of you're making sure you're always filling up that habitat piece. So these do not look like plantations, even if you did fairly aggressive removals.
At the end there, that if you lose money on selling
Right.
wood biomass for energy,
Right.
what would how much would the price need to go up for that not to be the case?
Well, you lose. If there was if there was a $10 a ton carbon tax or $20 it was a carbon payment, it'd make a big difference. But you lose money in the short term, but I actually interviewed one of the largest timber companies in California, and I did all the math, and I figured out they're losing money, and I called them and said, you guys never lose money, you cheat your truckers, you broke your union, what's going on here? And he said, we know what's going on. If we didn't lose $2 a ton, we would have had this fire risk if we tried to burn it on site or something else. So they basically said it's an investment in insurance that they were doing. They're willing to take it's a kind of investment in management that you had to move it. So, in areas, because when you do burn them, that's a lot of emissions. You burn up. So it's, the price might go up more or less the price is just like someone will take it. I mean, people are willing to lose money getting this stuff off their site. But if no one's going to take it, it doesn't go anywhere. That's our problem, is there's just no one within 50 miles that'll buy. We'd be willing to give it away, to lose $10 a ton, but if no one can buy it, then we're not willing to lose 30. So anyway, hopefully that was some interest to people that usually don't work in forestry and not too confusing. So, but that's it. So thanks very much.